This is the Pearson Edexcel AS Core Pure paper it's actually the sample paper. So just based on this book, and it's 80 marks, 1 hour and 40 minutes, or 100 minutes. Let's get straight into it. So first, we have the root question here. Now we look here and we see that we've been given information about the minus 15, so that's useful because it means that the three roots multiplied together make minus 15 over 1, except there's 3 of them, so we also have to shove a negative in there, which essentially just makes it 15, right? So because there's 3 roots multiplied, there's a negative sign in here, the negative cancels with that negative, this one doesn't matter, and we just get this. This alpha cancels with that alpha, this all just multiplies by 5 then. You can multiply all of this by alpha, you can also take away 15 from both sides. You can finally divide by 5, and you end up with a quadratic to solve for alpha, which you can do. Your calculator will give you this, which means we can now just assign, basically, 2 of these roots to be these things. I mean, I can definitely assign alpha just to be 2 plus I, for instance. And then I can work out what 5 over alpha is if I want to. Now, I sort of know that this must be a complex number. I'm obviously going to realize it. Thankfully, it turns out to be 2 minus I, which is the other root that I needed. And I could have just immediately said that here, because this was never turning into a real number, was it, from here? So it must be this one, because this one must be a root. Anyway, we can say alpha is this, we can say 5 over alpha is this. So what's the last root? Well, we can work that out by just shoving in alpha into it. So just put this alpha into there. I know 5 over alpha is this, so I can say this is 2 plus I, which is alpha. That's 2 minus I, as we just figured out, and then just minus 1 from it. That makes you 4, minus 1 is 3, these cancel, and you get 3. So the last root is just worth 3. And we have our roots, 3, 2 plus I, 2 minus I. Find the value of p. There's lots of ways to do this, but I think the easiest way would be to say p is the sum of the 3 roots. It's actually not quite. P over this with a minus in front is the sum of the 3 roots, because there's 3 of them. Again, it's a negative. When we add those up, we get 7, I think, over here. The i's cancel again, so p is minus 7, and we'll have our answer. Good, so question number 2. So we've got a point here, and we've got a normal vector to it, which is useful, because that means you can make an equation of the plane. A plane is given by this formula. You've got r, which just represents x, y, z, dot a normal vector, which you've been given, equals some number k. Now, if we know that this point here is in the plane, we can just put 5 minus 3 minus 4 in here and dot these things together to find k. And we get this, and we find k is that, which means this is the formula, or the vector form of the plane. But of course, in Cartesian form, we just replace r with x, y, z, and then just dot product out. So 3x minus y plus 2z, and we have our Cartesian form of the plane. Okay, now we have a line in vector form, and it says it intersects the plane at point x, which is cool, but it's first asking us to find the angle between plane and line. Now, to do that, we need to use this formula, which is not in the book, unless I've missed it. I don't think this is in the book. A represents the direction vector of the line, so this one here, not this one here. This is just a random point on it. And n represents the normal vector to the plane, which we already know here. So a dot n, we can just do. A is this, n is that. A dot n we can just say is minus 3 plus 5 plus 6, which is 8. And the size of n is this squared plus this squared plus this squared, which is that. And the size of this is this squared plus this squared plus this squared, which is that. And then we can do sine of theta equals 8 divided by root this, root that. The moduluses don't really do anything here. Do sine inverse of that, and you do get the answer that they want you to get, which is good. Find the coordinates of x. So what we can do here is we can say, well, this line has x coordinate 7 minus lambda. I've just put these 2 vectors together here, but this and r again is just x, y, z. So this shows us x is 7 minus lambda, y is 3 minus 5 lambda, z is minus 2 plus 3 lambda. You can just do that from here if you want to. Write those 3 things out, and where those intersect the plane, you can just put those x, y, z's into here, right? Just put those straight into the equation for the plane, and sort this out for lambda. Eventually you get this thing here. So they meet when lambda is minus a half, which means you can just put lambda is minus a half into here, and or into there if you've actually written this bit out. And you can work out your coordinates there. Good. Question number 3 then. So he's got 3 counts. I've called this one A, this one B, and this one C, just because I don't really care. And he invested £500 originally. So A plus B plus C, the amount he invested in each, is equal to 5,000. 400 more in property, so 400 more in B than in A. So that means B is 400 plus A. I'm going to write this really weirdly. I'm going to write it like this. And you'll see why. After 1 year, A had increased by this, so that as a decimal multiplier is 1.015a, b increased by this, and c decreased by that. So they've been very helpful to make that bold. And that's 79 more than the original amount, so that all equals this. And now I can put this line, and this line into a matrix. That's why I wrote this one so funnily. It's because I can now put it in a matrix with coefficients -1, 1, 0. And we'll get this. So that first line is this one, second line is this one, and the third line is this one here. And yeah, we can solve this because this is just a matrix full of numbers, which means I can find the inverse matrix literally just in a calculator. I haven't even bothered to do it because I know, essentially my idea is just front multiply this matrix by the inverse to cancel it, so this just all goes away. So we get ABC is equal to, again, multiply this on the front by the inverse matrix, and you can literally just put all this in a calculator and you'll get your answer, and you weren't expected to do that by hand or anything like that. So this just gets you full marks if you do it like that. Of course, you can maybe, just to be safe, because I made up A, B, and C, I might just be very clear about what my results are, and that'll be that. Question number 3 is about roots again. It's one of those super nice questions. We just say that maybe w equals x minus 1 because that's the change in the roots, which rearranges to x equals w plus 1, and you just put w plus 1 into here. And you just do a bit of expanding and cancelling and stuff, and you get your answer. 5 lines for 5 marks is very efficient. Really nice. Good. 5. Talking about matrix M. So non-singular. So we find the determinant. We just want to show that the determinant is 1 minus root 3 squared, which is plus 3, which is 4. That's not 0, so it's non-singular. So that's fine, and then we have hexagon transformed by M. All we need to know here is that when you multiply or when you scale a shape up by some matrix, it's the determinant of the matrix that is the area scale factor. So we have an area of 5, the area scale factor is 4, because that's the determinant of the matrix. 5 times 4 gives us a new area of 20, that's all we have to say. Matrix M represents enlargement, as we were just talking about, scale factor k, followed by rotation. Find the value of k. Now, its area scale factor is 4, which means its length scale factor is root 4, which is 2, and k is positive, so it's not negative 2, we don't have to worry about that. So scale factor 2, find the value of theta. So it scale factors up factor 2 in terms of length, and then it's a rotation by angle theta. What is theta? Well, the way that I did this, there's probably lots of ways to do it, but I always look in the formula book whenever I can. Here's the matrix that's about rotation. I actually don't think I ended up using this, but it's worth looking in the book. What I actually did, yeah, I didn't end up using this today, was I just took a point. I took the point 1, 0, and I decided to apply this matrix to it. Now, I know 1, 0, firstly you can multiply this out, you get this clearly, 1 and then 0, and then root 3 and then 0, so you get this. So the point 1, 0 goes to the point 1, root 3, which is up here somewhere. Now, I know when I enlarge with factor 2, the point 1, 0, we get to 2, 0. So if this, the matrix sends this straight to this, but if it's actually a thing that's doing one thing then another, I know it goes here first, because that's just scale factor 2. And then it rotates around to here. And all I need to know is what angle of rotation is that? Well, I just need to find this angle here that gets me up to that point. And this length is root 3 because of this, and this length is 1. So all I have to do is tan inverse of root 3 over 1, and I find that this angle here is pi over 3. And so the rotation is angle pi over 3. It's also good to check that this distance here is 2, and so is this distance, because 1 squared plus root 3 squared is rooted as 2. So again, this is a good rotation, and it's a rotation of pi over 3. So that will be our theta. Probably lots of ways you could have thought about that. So we're proving the result here that we all should know anyway, but we're proving it now using induction. So just set n equal 1, you get this, which is just, of course, 1 squared, which is 1, which I guess you could write with all these 1s in here, so this checks out. Cool, and then we're saying, okay, let's just assume that it's true for n equals k, where k is an integer, so we put k into here, and we put k into there, and we assume this is true. And then we check out n equal k plus 1, so we put k plus 1 up here. And the first thing we do, there's only a few different inductions they do. They do it with sums of series, they do it with indices stuff, and they do it with matrices. If you just know the trick for each one of those 3, you can basically always get these questions right. The trick for sums is you just sum up to the assumption bit, so sum up to k, and then split it out and do the last term, k plus 1, the input, on its own. So this by assumption step is just this, This is just you put in k plus 1, and that's the only term, so you just get k plus 1 squared. And now let's sort out this. Now I notice that there's a k plus 1 term in common, so I can drag that out. I can also drag a sixth out, just because I know I'm going to aim for that eventually. And then I can put a 6 over on this second term, just because a sixth times a 6 gives me the 1. Now this in here is just a quadratic, so I think I'm okay or just quite happy to expand it all out and collect together, and this factorizes very nicely into this. And now just to be super clear, I think I can write this bracket here as k plus 1 plus 1, and I think I can write this one as 2 k plus 1 brackets plus 1. I think that all matches, and this is of the perfect form, this, where you replace n with k plus 1. So what we've just established there is if it's ever true for n equals k, it's true for n equals k plus 1 if k is an integer. We know it's true for n equals 1, that was our first step, so therefore it's true for all integers n. Good, and that's part A done. Part B, use the standard results, which we can find in the formula book, to show this thing equals this thing. When you expand this out, you get r squared minus 36. So times by r is r cubed minus 36r. We can then break this out into two sums, of course, and we can put the 36 in the front because we don't need it. This we can just read from here. This you need to know. You're only given these two, so you need to know this is just n into n plus 1 over 2, which we can simplify. And then I can notice, actually, I can factorize out. I mean, look, I'm trying to factorize out a quarter, an n, and an n plus 1. Now I can see the n and the n plus 1 here, so I'll factorize out those. I'll also, just for the hell of it, factorize out the quarter and just leave behind a 72. A quarter times a 72 is 18, so that's good. And all I leave behind on this first time is n and n plus 1, and actually nothing aside from that number there. And now I can just expand out this bit in the square brackets, I think, and that factorizes to n, well, it factorizes the thing there, so you don't even need to think about it too hard, and we'll have our answer. Good, so the last step is to hence do this. Now we've just shown that this thing is that thing, so we can put that in, and this thing we can use the formula that we've proved and is in the book and put that in. I think at this point I times everything by 4 and times everything by 6. Nope, I didn't. What did I do? Oh, I noticed that n can't be 0 and it also can't be minus 1. So I'm allowed to divide by those two things and just get rid of them. I'm allowed to cancel them out because I'm not going to divide by 0 at any point there. And now I can times by 6 times by 4, I think, both sides. Yeah, I think that's what I did. And now expand everything out, collect everything together. Now this is a nice little challenge. You know that the solution must be an integer because this question is all about positive integers. So you could just put that in a calculator, or you could think, well, it's an integer. I could probably do this on my own. Divide everything by 2, of course, and then can you factorize this? Yeah, you can. I mean, you can, but the question is, can you do it? I can. I spotted this fairly quickly, and we'll get the answer of n is 25. Minus 3/10, of course, is not an answer that we care about. We just have this one here. Only a few questions to go now. This question is very long. It's a volumes of revolution question. Let's have a look at it. So we've got some kind of bird bath thing, which is all of this object here. And we've got this curve here is of this equation here between minus 0.2, sorry, and 0.2. We have these heights here. And we're suggesting the maximum depth of the bird bath. So the bird bath is this top bit here where the water, I presume, would be in. So we're looking for this depth here. Now, when x is 0, I think I can find what y is, just with this equation here. When x is 0, y is 1. So I think that's the point 1. And now if this whole thing is 1.16 high, I think that means the depth is 0.16, the depth there. So I think that's my mark there. Find the value of k. Well, of course, again, I can just do some values here. When x is 0.2, y is 1.16, and I think I can just put that into there, and I'll solve for k, I think, fairly quickly. I'll get k as 4, so I have that. So I know this equation now, hence find the volume necessary for this. Now, there's a couple of steps required here. Firstly, what I want to do is I want to integrate around this way, of course. Integrating around this way will do nothing, and that's no good. So I want to integrate around this way. Now you've got to be super careful here. You're so used to thinking that integration finds the area underneath a curve, right? But when you're integrating around this way, the volume of revolution that's going to be formed by this curve is actually going to be this kind of half-y circle thing above the curve when you revolve that around the curve between, I'm going to do it between 1 and 1.16. I'm going to revolve this curve, which is just x squared dy. I'm going to revolve it around this way, and we actually get this area in here. And then what I'll do is I'll find the area of the entire thing here and just take it away. Now x squared I can just very quickly arrange is y minus 1 over 4. I can bring the 4 out, so I don't care about that. Do the integration here, it's very straightforward, so we'll just skip through it very quickly, and we'll get some decimal. And now that's this area in here, the 3D area in here. It's not the area below it, because you can almost turn your head to the side and say I'm integrating this curve up to this y-axis, so I'm finding this area in 2D, and then I'm going to swivel it around and I'll find all of this area here. So just be careful to not do this on autopilot and just think, oh, I'm doing the area under the curve, and then, yeah, sure, you're doing this area here. So now I can take away all of this area, which is, or this is just a cylinder, isn't it, when you swivel it around. So it's radius 0.2, height 1.16, the area of a cylinder, sorry, the volume of a cylinder is pi times r squared times h. R is this, h is that, that's this, and so now we're going to do this cylinder minus that thing we found down here, take those away, and we get this figure here. And that will be our answer. I think state of limitations, yeah, I mean, there's lots of things you could say here, I'm sure. They might not have measured this super accurately, is one, cool, fine. It's later discovered the volume was actually this. So our volume is this that we found, it's actually given this. Now, I don't really like this question, I don't really understand the answer that's in the mark scheme, but one thing you could do is you could find the percentage difference, which we all know how to do, so let's take away this over this times 100. So it's a 7% difference. Now, I thought, when I did that that was quite good. That seemed like quite a good stat, but the mark scheme says, oh, model predicts 7% more than needed. Not a good model, that's what it says. So maybe this is just good for future reference, is AS or A-level mark schemes consider 7% to be not good. So maybe that's a good thing to keep in your head, and when you do this in real papers, if you're below 7, maybe you can get away with saying it's a good estimate. If you're above, then you definitely can't. Maybe that's a good thing to keep in your head. I thought 7% was fine, to be honest, but yeah, I don't know, whatever. So yeah, we get to a proper maths question again. Now, so this is a circle, center 4i, radius 3, so that's nice and easy. And this is 2 half lines. Now this is written wrong, right? We'll put a minus in there. So the lines originate at minus 3 plus 4i, and one goes off in the direction minus pi over 2, one in the direction pi over 4. So when we draw this, circle center 4i, radius 3, 4i means that radius 3, it doesn't drop to the axis, like this distance is 3, this distance is 4, so it doesn't drop to the axis, so that's my drawing there. Now this is minus 3 plus 4i, now that's already 4i there, so this is nice because that just puts it right there, this point. And now we have a line pi over 4, which is gradient 1, right? This is gradient 0, or sorry, this is angle 0, this is angle pi over 2. So angle pi over 4 is exactly in the middle, it's this way. And then angle minus pi over 2 is just back this way, straight downwards, so we got there. And we need to be inside the circle, and we need to be in between the two lines, so I think we need to be here. Come to think of it, oh, does it matter? I just noticed this, which I didn't notice before. I don't think it matters. This means you can be on the line, so it's good that I haven't dashed that. I maybe should have dashed this, but it doesn't matter because you're allowed to be on the circle, and this line doesn't. It's not any boundary here anyway, isn't it? So that's fine. I think we're good there. I think I've done it right. Anyway, that's the 6 marks, I think. So yeah, good. Next, the complex number satisfies this. Now this is the same as this. We're on the circle, so we're a complex number on this circle. Find the maximum argument in this interval. So we need to find the complex number on this circle with maximal argument. Now argument is measured from the origin with the positive x-axis. So this argument here is quite small. If we chose this point, this argument is quite small up to that point. The biggest argument we can choose is the one that goes out this way and just touches the circle over there. This is the biggest argument that we can pick, I think. So okay, how do we find that argument then? Well, we notice that this distance here is 4, straight down to the origin. This distance here is 3, because that's the radius of the circle. And we can find this angle here by just doing sine inverse of 3 over 4, opposite over hypotenuse. This is a right angle, of course. That equals that in radians, and then this is all animated in immediately, but this angle here is pi over 2, of course. So we just need to add that into this angle here that we found, and we'll get this answer here, which is all of this argument there. And we'll have our answer, I think, correct and done. We've got one question left, which is another vectors question, the second question on the paper. About vectors, we have a fish swimming in a straight line on modelled as a line, and an octopus modelled as a point sitting at the origin O. Fish modelled as a line. Fish goes through these 2 points. So the vector equation of the fish's trajectory or movement is just pick one of the points, so I picked this one, and then plus lambda, and then you've got to get 12 along from minus 3 to 9. It's another 3 from 1 to 4, and then it's 18 from minus 7 to 11. So just pick how far you have to go from one point to the other, and just put it in there. That's the vector equation of the line. I think that was 2 out of the 7 marks, if I noticed correctly. Anyway, and yeah, now we need to find how close does that line get to the origin, is the question. There are lots of ways to do this. The way that I chose to do it was I just wrote this as its x-coordinate is minus 3 plus 12 lambda, its y-coordinate is 1 plus 3 lambda, and its z-coordinate is minus 7 plus 18 lambda, all I said was the distance from the origin to this point is just Pythagoras. It's just the root of this thing squared plus this thing squared plus this thing squared, and I just aimed to minimize that. I just wanted to know when is that at the minimum, right? Because if I knew when it was at a minimum, I would know whether that's within 2 or not. So let's just minimize this here. So just Pythagoras here, squaring them all out. Now, of course, the square root here doesn't really matter, because if you're trying to minimize this whole thing, you just want to minimize the thing in the square root, right? So I'll just ignore that, and I'll expand all this out. I'll collect the two all together, and my aim is to minimize this. There are lots of ways to do this. I just chose to differentiate. So I differentiated to find this and set it to 0. And just solved to get that lambda is a third. So I know that this distance is at a minimum when lambda is a third. That's what I found. I haven't technically discovered whether it's a maximum or minimum or anything like that. I also can't be bothered. You can very quickly do that if you want to, but put lambda as a third into here, and we find this, right? Minus 3 plus a third of 12 is 4 gives you 1, and then 1 plus a third of 3 is 1, which is 2, and so on. And that's the closest point to the origin that this line ever gets to. And so we can just do another set of Pythagoras to find how far away that is from the origin, and it's root 6 away, which is bigger than 2, so no, the octopus will not catch the fish. Criticize the model in relation to the fish. It's very unlikely that it will swim in a perfectly straight line, so fine, yeah, that's our criticism. And criticize the model in relation to the octopus. The octopus is supposed to be sitting at a fixed point O. You'd think that it might move occasionally, maybe. So yeah, we'll just say that. And that's the whole paper, I think. So thank you so much for watching.